Thank you for kind introduction. Good morning, everyone. I come from the Joint Research Center in Karlsruhe, so located in Germany. But the Joint Research Center is one of the 6 research organizations of the European Union, and we are, let's say, 100% nuclear side. So looking at the properties of nuclear fuels, safety of fuel cycle, things related to that. So I would ask, is there also someone who deals with nuclear in this room, or it's all non-nuclear? Yes, partially. So I don't have to make the longer presentation about nuclear. No, I can stay with the short one. Yes. Very good. So there was also feedback about oxides. So we also work with oxides because oxides are, let's say, the traditional compounds that are used in power reactors used nowadays. But molten salt reactor is a bit unique, is a bit different. It's a future reactor concept, although it has been already built in the 60s in United States. But today it's considered as a future concept. Many companies embarked on that in the past. I will show that a bit. But what it is, very briefly, the salt is, I mean, the fuel is not solid, it's a liquid. It's pumped through the reactor core to the heat exchanger and back. So the salt systems allows quite big variety. So this also gives you a bit, let's say, idea what the database, what systems there are in the database. It's always a matrix, and then there is some fissile material dissolved in it. So normally those are halide systems, very similar systems that maybe the what is this FactSage database on halides on ionic liquids. But in this case, we also combine it with fissile materials because we want to look at the fuel properties. So the fissile materials is uranium or plutonium. But also we can look at other actinides, but mainly it's plutonium and uranium. And you see here on this slide variety of different concepts, and our goal is to develop database that describes these systems. In principle, no matter from which company, which country the interest comes. Of course, the major interest is in Europe. But the idea is to also have insight into properties of, let's say, other concepts. So you can see some past concepts, mostly based on fluorides. The last one there is MSFR. That's a French concept that we've been busy with, let's say, last decade and something. But nowadays we are shifting also the attention more towards, or the companies towards fluoride. So actually, in principle, the database I'm dealing with or talking about is dealing with fluorides and chlorides. And variety of systems. This gives you a bit. I'm happy to actually present this slide today because normally when I present this slide, the first question is whether everyone can read phase diagrams. I would be very embarrassed to give this question today at this meeting, so I can go straight to a bit why, for instance, how we utilize the phase diagram. So this gives you a bit just few examples that some systems are rather complex, the others maybe not that complex when it comes to certain fuel systems. But what is normally why we take advantage of these, let's say, the full description of a particular fuel system is that once we have the full description, so we have these polythermal projections of liquidus, that guides us very quickly to the lowest melting point. And lowest melting point is normally or you want to have the fuel with as low melting point as possible, because then also your operating temperature of reactor is broader, and also you don't want to overheat your reactor so much, because then there start to be also corrosion issues. I think everyone who deals physically with halide salts, the corrosion at certain moment kicks on. Of course, there are special structural materials, but it does the kinetics does play a role there. So you want to stay as long as possible with the melting point. So the phase diagram description, of course, is very useful, because one thing is to have a low melting point, but the other one is, of course, addressing other properties. I come back to that, but also the neutronics. You have to have enough material, for instance, plutonium or uranium, whatever your fissile material is, so that you can even run the reactor. So this is very useful tool to have this interaction between neutron physicist and the thermodynamist in this case, to have this very let's say useful play back and forth. So that gives you some idea. And for instance, this complex system is when you start adding fission products, because one thing is that we want to address is what are the properties, what are the phase equilibria of fresh fuels. But another thing is when you start your reactor, you start to form fission products, because uranium or plutonium splits into different fission products: lanthanum, cerium, zirconium, or gases, xenon, krypton. And this is all or some of them are accumulated in the fuel salt. So our goal is to expand the database also to looking at these equilibria and to be able to understand what's happening with the fuel in the course of lifetime. And another part is, for instance, these are our measurements. We also combine, I will also show you on some slides next, but we don't do just the modeling, but we want to get a solid modeling. So we first do some experimental data points. So for instance, phase diagram investigation systematically, and then we fit the phase diagram through. So this is, for instance, one of the earlier studied system, lithium fluoride, thorium fluoride system. And once we get the description, it is very well known to everyone in this room, but I just want to point out why, to motivate behind, is also that other properties can be well derived and relevant properties for reactor designers or safety authorities, like what are the phases, what's the melting point of that particular point, what would be the boiling point, what would be the vapor composition at certain temperature, the heat capacity, of course, plus also other thermodynamic quantities that are then relevant more for those that dealing with modeling. But for instance, enthalpy is also extremely important, because people want to know how much heat they need to input to melt the salt before they can run the reactor, and of course vice versa. Another thing is also not to be neglected. For instance, what is your first crystalline phase formed from your fuel composition? Because in this case, it's a very simple example, but if you have something more complex and you might have something precipitating that has high content of plutonium or uranium, you might form hotspots in your reactor under certain undercooling scenarios, and you want to avoid this. So I think the knowledge about this is extremely, extremely important. So about I think I skipped one slide. Yeah, there is one slide missing. Okay, then I go directly to the model. The slide I was missing was actually to show you how the database has been developed in course of time. So I can just briefly tell you, we started with the molten salt reactor campaign at JRC in 2002. So that's 23 years ago. At that time, it was ran by one PhD at the time. We had 5 PhDs, so 15 years just running, and we were developing from scratch, taking something from the literature, but the effort was mainly on actinide containing systems to add more data and add it into database. Then in the meanwhile, okay, Fukushima came. Of course, there was a big hit on the nuclear program worldwide, but it didn't really affect that molten salt reactor R&D in our institute, because it was very, very low. I mean, one PhD at a time was not really much. But in around 2020, we also, let's say, the molten salt reactor technology attracted a lot of different small enterprises, startup companies, but also major companies like Orano. Orano is the major fuel producer in the world, a French company, and they are looking into this a lot. And we started to have also commercial contracts. And today, last year, we signed a collaboration agreement between Delft, us, JRC, Orano, and CEA France to co-develop this database. I will have one slide on that to also show that it's open for other collaborators if someone is interested. So that's just a bit brief overview about that. The model that we use for the liquid phase is the modified quasi-chemical model that has been developed by the Montreal group, and particularly by Molten and collaboration with Chartres. So there is a series of papers. I have here one reference. Very briefly, it's based on quadruplet approximation. Not going much into detail. We will have a very nice talk of Anna Smith, which is coming next, about dealing with the model more. Why did we decide about this model? Well, there were two reasons. We were also playing a bit with polynomial formalism before, but it does not really reflect the real structure of the salts. And we wanted to be also a bit more realistic. We had Raman spectroscopy plans coming, so we wanted to also combine that type of experimental work. But we had also collaborations starting at that time, 2005, 2004, when we decided about this model, and then we wanted to be compatible, of course, with them. And I think Alex was one of the person that we discussed at those earlier stages. And I would give you at least half credit for us to select this model, maybe 51%. So I will not discuss more about that. It's just that this model also allows a bit speciation in your liquid phase. And this is important that you can translate this indirectly afterwards into other properties like viscosity. But again, there'll be a nice talk of Anna Smith from Delft later on speaking more about that. So this just shows you that we do the modeling, we develop the database. It's kind of like the picture here on the up right. But I always say, I don't know if you would agree all with me, maybe 80%, but that to have a good model, we also need to have a good some evidence, experimental evidence, so that we can actually fit the model well against something that we grasp in a real life. So experimental data. So also we have facilities to measure thermophysical properties. Many of them that are listed there are related to thermodynamics, so to the model. But we also need to have a facility to synthesize the salts, because if we don't synthesize the salts, we cannot measure them. That's very simple. So we have also a strong group domain to do this on the lab scale, so that we can then perform the measurements. And one more thing that I want to highlight is also that we are involved in irradiation experiments, and that comes, for instance, to these interactions or equilibria with fission products, because it's a kind of, you can imagine that takes maybe 5 years from making the fuel, irradiate, sending back, and make analysis. But then that's very useful to, for instance, validate the database. So that's also something that we like to do, the validation, because especially when you extrapolate higher order systems, the validation is finally the key to see whether we are at the right extrapolation or we need to modify by higher order parameters, for instance. So that just gives you also a bit a picture that we really have the experimental facility series of glove boxes, because we work with actinide. So this is all or selected equipment that we use for the thermodynamic studies at our facilities. Then this gives you a bit overview about the database. So we are about today 120 pseudo-binary systems. So you see the big domain in fluorides that was more or less mainly done in past, but still we work on it. For instance, improving the sodium, potassium, uranium fluoride system. But attention is given on chlorides, as I said, and nowadays because of slightly different reactor concepts. So we are also expanding in that region. So we are about 120, still trying to look at the key systems and different variations. So it's, I think, solid size database, not as big as Moritz was explaining. I think the first day that the liquid is 1,000, but we don't have competition here. Just make it clear. It's So it's pretty extensive. As I said, it's now a collaborative effort. But what is important is that we also work together with GTT to distribute this as open access database. For this, of course, I can take the files and distribute it. This is not a problem, but we need encryption for two reasons. One is preventing duplication. I think that's clear to everyone who deals with databases, but the other one, quality assurance. If we put something in a database, we want to keep control on the data, and if someone can modify this data, then still claiming it's JRCMSD database, but with wrong data, and it's very difficult for us to keep track afterwards. So these are the reasonings behind. We had already some not the best experience when we give it someone with open data. So that's a bit another burden we have to put in place, but certainly needed step. That took also some legal documents that we can, as European Commission, distribute this database, because the IP is with us. And you can imagine it's a nuclear database, so there can be also some restrictions to certain countries. Not going much into details, but for this we need some legal documents in place. This will be distributed through EU Science Hub. So I'm working on it to physically really place it there, and I hope this summer it's gonna be available. Then I don't know if there is someone from North America here. Yeah, you. Okay, so there is it will be supported with FactSage, this database. That's why we deal with GTT. For North American region with the user IDs, it's a bit tricky, but there are options how to do it. So it's also on the way. And this is the last. I don't know what time, how much time I spent already. I started my start clock, but I have 000, so that's probably not 1 minute. Then I say this, and I had some examples. I will not go into them. This is something that I want to advertise as we are now expanding. We have also now open position for a contract agent at JRC. It's up to 6 years. So that can be attractive for someone starting a career in nuclear or being after a master, after PhD. So the link, I think if you have access to the database, it works. If you copy it, it should work. And then it should drive you to this page. And I think the deadline is now 27th of June. So if someone is interested in working with us on this database, it would be a combination of both the database management, the modeling, mainly keeping track that everything is well in place, but also you would have access to the lab to do some experimental work where needed. So it's a bit combination of both, because we as I discussed today, we do both. So with this, I would thank you for your attention, and I stop here. Thank you.